Alright, so this time we're doing problem 54 from chapter 6. And the problem says, a 20 kilogram rock is sliding on a rough horizontal surface at 8 meters per second and eventually stops due to friction. The coefficient of kinetic friction between the rock and the surface is 0.200. What average power is produced by friction as the rock stops? So, we're looking for power. We know that power is going to be equal to the work divided by the time. And this is going to be the work of friction, because it's friction that's stopping the rock. We know that the work of friction is going to be equal to 1/2 mass times velocity squared. But we also need to find the time. So there's a couple of other equations that we need. We need that the final velocity is equal to the initial velocity plus the acceleration times the time, and we need that the net force is going to be equal to the mass times the acceleration. Because we need to find the acceleration here, to find the time, we can then use the time for this time over here divided by the work divided by the time, and that'll give us the power. So, we first need to find the acceleration. So this equation can be rewritten. We know that the force is just going to be the force of friction that's stopping the rock, so that's going to be the coefficient of friction times the mass times gravity. That's going to be equal to the mass times the acceleration. So we know that acceleration is going to be equal to coefficient of friction times mass times gravity, all divided by the mass. So we can cancel the mass there. And then you just substitute your values in. So 0.200 times 9.81, and that gives you an acceleration of 1.96 meters per second squared. We can then use that in this equation, so we know that our final velocity is going to be equal to 0. Our initial velocity is 8 meters per second, plus our acceleration that we just found, times time. So then our time is going to be equal to the absolute value of 8 divided by 1.96. And I do the absolute values because doing the math, I find that, the acceleration probably should be negative. And if you do that as a negative, that'll then cancel out the negative from subtracting the velocity to the other side when you're isolating for t. But when I originally solved it, I just figured we're probably not getting a negative time. And so we actually don't need those, because the negatives will cancel out. Because it would be a negative and a negative. And so you get a time of 4.08 seconds. So then we can substitute all of this in for the work in our power equation. So we can rewrite that as our power is going to be equal to 1/2 the spring constant times the velocity squared. No, not spring constant, mass. Mass times the velocity squared divided by the time. We then plug in all of our variables. It's a 20-pound rock. It's going at 8 meters per second squared divided by 4.08 seconds. And when you do the math, power is 157 watts. That's how you solve the problem.